you need to notice that from Young's double slit experiment, the central bright fringe, I mentioned it yesterday as well, the central bright fringe will have the maximum intensity of light. And as you move from the central bright to the first bright, you are covering a certain distance. And when you cover a certain distance, the intensity is inversely proportional to the distance. So the intensity of light would decrease. The distance, as the distance increases, the intensity simply decreases, such that there's an inverse square relationship. Please understand that intensity is directly proportional to a square. These are direct numericals. Let's say, for example, if I were given two waves, one is wave A, right, having an amplitude of 2 and has an intensity of I, you are asked to calculate the intensity of wave B in terms of I. So using this, you can check off that intensity is the square of amplitude. From math, you know for a fact that as I remove the proportionality sign, there's a constant that comes in, right? And as the constant is here, this intensity I, you need to work it off for K. So K would be equal to I upon 4. What you need to do is that from wave B, they're saying, again, intensity is equals to Ka squared. It's the same type of wave, so the K value should stay the same. The intensity for wave B is considered or said to be Y. K has the value I upon 4, and the amplitude of wave B is 5, right? Simply put in the value. So X is equals to 25 upon 4 of I. And that is how you actually work off questions like these. These are very straightforward questions. They won't confuse you with these. They can tell you there's constructive interference, there's destructive interference. You need to understand that for constructive interference, your amplitudes would simply add off. For destructive interference, your amplitude decreases, right? This is a very important concept that I want you all to understand. When we were talking about crests and crests, we would simply say that the 2 points are in phase with one another because of the fact that they had identical behaviors, right? If 2 points are exactly opposite to one another, for example, crest and trough, they were out of phase to one another, right? But what if on a wave, let's say you were asked about this point, and let's say this point. Now you need to understand that when there is any random point such that it is not either in phase, not out of phase, meaning to say there is no proper phase difference value, right? We use the concept of leading and lagging. Before I move on, I want you to understand something. If 2 people are about to run for a race, this person A, this person B, both are about to run for a race. The race starts, the person B runs off, whereas the person A is standing still there, processing what has just happened. You'll understand that A has crossed off a large distance, meaning to say that, B has crossed off a large distance, whereas A stands still in the position. that is the 0 mark, right? Let's say at any certain time A is at the starting position and B has crossed off a certain distance. You can simply say that B is leading the race, whereas A lags, right? So waves work in exactly the same way. The wave that starts off at an earlier time, meaning to say the wave that starts off before or is ahead in time, right? Meaning to say the wave that has crossed a larger distance or has worked on a shorter time is the one leading the race as compared to the other one, right? How do they give you a question? Let's say you have wave A, right? That was given to you. It's a graph drawn. You need to understand that each box corresponds to a unit of 1. Right? Each box corresponds to a unit 1. You are told that you should construct a wave B which has thrice the intensity and which lags behind A by a phase difference of 60 degree. Before we move on, please understand that wave A has amplitude 2 units. So intensity is equals to K A squared. Intensity is equals to K times of 2 squared. And you can simply work off that your K value from here is I upon 4. Right? For wave B, they tell you that again I is equals to K A squared. You need to work off the amplitude. You need to work off, you're working off wave B here. Right? So wave B is such that it has thrice the intensity. The K value is I upon 4 and your amplitude comes out to be squared. Your I cancels off and you'll understand that 12 is equals to amplitude square. And when you underroot that, you'll approximately get a value of 3.5 for the amplitude. And you know that wave B should have covered 3.5 units now. Please understand that they tell you that wave B is constructed such that it lags A, it lags behind A by a phase difference of 60 degree. Now you need to understand that lagging, wave B is lagging, meaning to say it starts off at a later time. It is shown here, but you need to work off how. Please check that for the entire wave, you have covered 6 boxes. When one complete wave forms, we say that a phase difference of 2 pi or 360 degree has been covered. So 6 boxes will correspond to 360 degrees. When you need a phase difference of 60 degree, you'll understand that you are getting 1 box. And therefore wave B will start off 1 box later. Next comes in diffraction grating. Diffraction grating is basically you could say a plastic material or made out of glass. Right? This diffraction grating has small holes. Right? By the way, you need to understand that plastic does not allow light to pass through them. These narrow holes will allow light to pass through them. And when light passes through them, light moves in a straight line. It seems as if there are lines coming out of these holes. So these lines are also called, these dots are also called lines. And the distance between each one of them is called grating spacing, right? So diffraction grating is an optical instrument constructed either using a glass or a plastic. This instrument has microscopic slits and is also called, which are called lines and are closely spaced out. The gap between these slits or lines is called grating spacing. The manufacturer of these diffraction grating will provide you with the value of the grating spacing. The intention of this device is to show spreading of light. Therefore, when light is allowed to fall on a diffraction grating, it spreads out. And if a screen is positioned in the background, the spreading of light can be displayed on the screen as illustrated. There's just like Young's double slit, there's a central order diffraction, there's first order, there's second order. However, the formula used is a little different. We have n lambda is equals to d sine theta, right? It's a straightforward question, so shouldn't be a problem. Next part comes in stationary wave. Stationary waves, like we discussed previously, are the ones where there is no net transfer of energy. So let's say if this is a barrier, the wave travels such that it reflects and cancels off. And therefore you will notice a straight line forming again because the incident wave was cancelled off by the reflected wave. And hence we say there is no net transfer of energy. As I mentioned, stationary wave will have only 2 points. Points having zero displacement are called nodes. Points having maximum displacement are called antinodes. For example, let's say I had a sound beam being produced, a sound wave being produced. At the node, you would hear nothing, literally nothing. But at the antinode, you would be hearing a large amount of sound. Right. So let's say for example, I have a forced oscillator here, and this is a reflective. The distance from the forced oscillator to the reflective surface is somewhat 2 meters. Before we move on, please understand that in stationary waves, node to node, the distance from node to node is equal to half lambda. How do we come about this? If we have a complete wave, that forms one wavelength, right? So two nodal points would have half a wavelength between them. Right. So you need to understand that I am setting up the frequency of this forced oscillator from 0 to a certain value, let's say ft, or let's say I'll call it a special value ff. The forced oscillator was initially at 0 frequency, and I had set it off to a certain value ff, and I realized a wave was being formed. There was a node at this end and there was a node here. Don't you think it is okay to say covering of 2 meters here, right? From here I can say that the wavelength would be 4 meters. I'm provided with the velocity of this wave, which is 600. I can calculate the frequency. Let's say the value is coming out to be 150 hertz. This is the lowest value at which a stationary wave was being formed, and therefore we name it as the fundamental frequency. Now I am increasing, for the next case, I am increasing my forced oscillator. The frequency of the forced oscillator is now increased to a value FO. I will have to notice the fact that one entire wave was being formed. Node to node is half lambda, and this another node to node distance. So you multiply this by 2, or you could say half lambda plus half lambda. That gives you lambda. Your entire wavelength again covers the distance of 2 meters. You're provided with the velocity value, which is 600 meters per second, and you will realize that your frequency comes out to be 300 hertz. This is the second value. This is the second value at which a stationary wave was being formed. We call this the first overtone. Again, I'm increasing my frequency to a certain value, and this time I felt that there are 3 node to node distances such that my wavelength becomes 3/2 lambda. The entire distance was fixed at 2 meters. I could work off my wavelength and therefore calculate the frequency, 450 hertz. This is called the second overtone. You need to understand one thing. I initially calculated the fundamental frequency and I kept on thereby increasing the frequency values, and I realized that the first overtone is a multiple value of the fundamental frequency. 150, your first overtone is at 300 hertz, your second is at 450 hertz. All of these are multiples of the fundamental frequency. And from here, we could establish the fact that stationary waves will be formed at specific frequencies. Not all frequencies are able to produce a stationary wave. That to produce a stationary wave, the following arrangement can be used. A string is connected in a manner such that one end of the string is connected to the oscillator, whereas the other end is made to be a fixed end. The oscillator can be made to vibrate at a particular frequency by connecting it to a signal generator. Signal generator is a machine, you could say, or a device that is used to fix certain frequencies, right? That's used to produce or increase the frequency values. When the signal generator is switched on and its frequency is set at a particular value, it can be noticed that the string will give rise to an incident progressive wave. These waves will travel from the oscillator towards the fixed end, and upon reaching the fixed end, they get reflected, and this gives rise to a reflected progressive wave which travels in the opposite direction, thereby cancelling it off. The superposition of these two waves will give rise to the formation of a stationary wave, thereby becoming zero. They are termed stationary because it appears as if the wave is neither traveling forward nor backwards. That is, the energy of the wave appears to remain confined within a loop. So there is no net transfer of energy. In a stationary wave, there are certain points known as nodes which exhibit zero displacement at all times. Midway between the two nodes are the antinodal points which exhibit maximum displacement. The distance between two successive nodes or two successive antinodes in a stationary wave is equals to half a wavelength. It can be shown that for a given length and for a given speed, there are only certain frequencies at which a stationary wave appears. The frequency is And all fundamental frequencies are called the overtones. Let's say you are asked to observe a stationary wave using electromagnetic waves, right? Now, you can literally not see an electromagnetic wave, right? So you allow the stationary wave, the electromagnetic wave, to form a stationary wave, right? And you move your detector from left to right. Areas with zero displacement are your nodal points. Areas with maximum displacement are your antinodal points, right? So this is what I've written here. When the detector is moved from the source towards the reflector, the intensity recorded continuously varies between maximum antinodes and minimum nodes. You have to measure the distance between two successive zero intensity points, or you could measure between two maximum successive points as well. And thereby you could equate it to half lambda. Let's say whatever the distance was, you're equating it to half lambda, right? And from here, you can thereby work off the frequency value. Comparing amplitudes in a stationary wave. Comparing amplitudes in a stationary wave. If 2 points are at equal distance away from the respective nodes, they will have identical amplitudes. Different points in a stationary wave have different amplitudes. Next point, comparing phase differences in a stationary wave. In a stationary wave, phase difference is compared on the basis of where the particle is positioned. All points within a loop are classified in phase with one another. Let's say this entire thing is your one loop. All of the points lying in here are in phase with one another, having a phase difference of 0. Points located in the neighboring loops are classified to be out of phase. So point A and point B has a phase difference of pi. Points in alternating loops, we are talking about this and not this. Points in alternating loops are classified to be in phase, having a phase difference of 2 pi. And again, out of phase, phase difference 3 pi. Differences between a progressive wave and a stationary wave. In a progressive wave, energy is transferred along the direction of propagation. In a stationary wave, there is no net transfer of energy. Therefore, energy remains confined in a loop. In a progressive wave, all points have the same amplitude, right? Where stationary wave will have different amplitudes. Neighboring points in a stationary wave have a phase difference of 0, whereas neighboring points in a progressive wave will have a phase difference, will have some phase difference, like this point and this point. Moving forward, investigating waves using some sound, let's say using a loudspeaker. The arrangement shown below represents a loudspeaker, somewhat like this. This is the arrangement, right? This is a closed tube, right? The velocity of the sound is provided to you, and you need to understand that one end of the tube is closed while the other end is open. The loudspeaker is connected to a signal generator, and when the frequency of the signal generator is set at a particular value, the incident progressive wave travels from open end towards the closed. They get reflected and travel in the opposite direction, just like the initial initial stationary wave we talked about, thereby giving rise to a stationary wave. At the closed end, this is important, a node is formed because the molecules have minimum capacity of performing motion, whereas at the open end, an antinode is formed. Open ends will have antinodes being formed. They will give you questions related to this. So please, that is why I've highlighted this. The lowest frequency is again the fundamental frequency, and when the frequency is increased, there are overtones. See, okay? Just like the initial case, you're provided with the distance node to antinode should be 1/4 lambda, and you equate that to 4 meter, right? And from here you can work off that your wavelength is 16 meter, and thereby you can work off the fundamental frequency and hence the overtones. Now the last topic, Doppler's effect. Doppler's effect is considered for situations where sound keeps on varying. Let's say, for example, you're sitting in a car, there's an ambulance approaching you. As soon as the ambulance approaches you, you can sense its voice to keep on increasing. And as soon as it crosses you, you will hear its voice diminishing. You are the observer, and from your respect, this sound value is changing. However, the ambulance gives out the same sound frequency throughout, right? In such scenarios, the Doppler's effect is used. This is the Doppler's effect.